This is just gonna slide right off, eh? All right. Hi, I'm Aleksa Bjelogrlic, and I've been designing a completely open source oscilloscope from the ground up for the last 5 years. Specifically, this oscilloscope. It all started when I was with my friends at the university pub debating an idea of mine. What if an oscilloscope could stream out ADC samples at speed, at least 1 gigabyte per second of data, to a computer for triggering, processing, and display? They convinced me a modern CPU could handle it no problem. If this idea would work, I'd build a scope that brings memory depth up from tens of megapoints to, well, as much RAM as you're willing to throw at it. Likewise with waveform update rate and your processing power. And since everything is done in software, you can easily add custom triggers, protocols, and other features. Like anyone with a collection of old test equipment, I know the analog stuff stays good, but the digital stuff is what doesn't always keep up with the times. So fundamentally, the idea is to put all the good analog stuff in a box and offload all the digital stuff. This could make for a scope that actually gets better as you upgrade your computer over the years. So as a second-year engineering student with a whole 3 circuits courses under his belt, I decided to get started on a prototype, thinking, how hard could it be? I may have bit off a bit more than I could chew. But about a year and a half of evenings, weekends, and irrevocable psychic damage later, I got sample data out of this thing. But this design had 2 problems. It wasn't transferring data fast enough to the computer, as it could only do 350 megabytes per second through USB 3 Gen 1, and I needed 1 gigabyte per second. And the front end wasn't fast enough either, along with a slew of other issues. So I switched over to PCIe, which could handle 1 gigabyte per second without breaking a sweat. And I improved the front end design. This is also where the project was reborn as Thunderscope, a Thunderbolt connected oscilloscope. That was a PCIe card. Rev 2 had a lot of changes. Too many changes, in fact, and I never quite got this rev working. First of all, I decided to mount a Thunderbolt to M.2 adapter on the bottom of the main board and use a cursed interposer to connect it. Believe it or not, this was the easiest way to get Thunderbolt on this design. Thank you, Intel. You'd think that that would be the culprit, but like any good mystery story, this highly suspected change was a red herring. I also overhauled the front end and used a new clock generator to provide a reference clock input or output that can be used with a synchronization signal to chain together multiple scopes. Rev 3 had a lot of little changes from Rev 2 and improvements to the front end. It also had the same issue as Rev 2. But this time, I had enough clues to crack the case. It was the ZL30250 in the ADC clock domain with an AC LVDS output, meaning the clock generator's output amplitude was too low for the ADC. A temporary fix was to remove its termination resistor, and since I got this rev working, I sent a few of them out as alpha units and even used it as an excuse to buy a Steam Deck. Should I say a scope deck? Rev 4 moved the front end relays face up into attack position and used a different clock generator. This is the latest version out there and worked well enough to send out as Beta 1, with Rev 4.1 on its way for Beta 2. Hopefully the last step before production. Not the first time I said that. Now, there's so much more to how this project got to this point, especially our contributors, Frederick, Mark, Entropic Engineering, John, Sabrina, and Ersino, as well as 2 whole other open source projects, LightX for FPGA cores and ng-scope client that we use for GUI and post-processing. With the background of this project out of the way, onto the main topic of today's talk, oscilloscope front ends. Now, why did I want to do a whole talk on just one circuit? Well, you don't need a spool of red string to find the pattern of changes between all these designs. and that's just what made it on the main boards. I've made about a dozen revisions of the front end so far. Over the years, I've encountered hardware issues so weird that it would make Occam ditch his razor for a Rube Goldberg machine. And now I get to share them with you. But first of all, what is an oscilloscope? Wait a minute, you're wearing one right now! On the most fundamental level, you take in an analog signal, digitize it with an analog to digital converter, send the data over into a circular buffer, process it until you find something matching a condition called a trigger, usually a rising or falling edge. Then display the samples in the circular buffer around the trigger point. The badge uses a direct input into the ADC, but if you were to add a front end, it would be here, between the inputs and the ADC. So why would you want a front end? To use standard passive oscilloscope probes, to use active probes, or directly connect to a 50 ohm system, to look at AC signals and a large DC voltage, like power supply ripple, to measure signals larger than the ADC can safely handle, and to make the most of your ADC's resolution, like using optical zoom versus cropping the image for digital zoom. How do these features turn into requirements? Your typical passive probe expects an input impedance of 1 megohm in parallel with 10 to 20 picofarads of capacitance. The fact that front ends range in capacitance is why you have to compensate your probe for the specific scope you're using. We'll also need some way to set the input impedance to 50 ohm, and somewhere along the path to switch in an AC coupling capacitor. High voltage signals need to be brought down to a level the ADC can handle. So we also need to be able to switch in a voltage divider. If the input voltage is too low, either directly or after the attenuation stage, the front end needs to apply just the right amount of gain to bring it to the voltage the ADC expects. And for the really small signals, we need to crank the gain all the way up. A good front end will do all of this while adding as little noise as possible to the signal over a large bandwidth, and keep a flat response from DC to that bandwidth. That's a lot of stuff for one circuit to do. In fact, I have painful lessons learned for each one of these requirements, and they all involve either noise, bandwidth, or flatness. Normally, when you're designing for wide bandwidth, you try to eliminate any stray capacitance. But a scope input needs capacitance in high impedance mode in order to function with passive probes. This is a schematic of a passive probe, and we see that our scope input impedance is part of some sort of divider. Specifically, this is called a compensated divider, and will come back to haunt us later. To be able to accurately set the input impedance, you want an input buffer with an order of magnitude higher input impedance. So my first attempt used a really fancy high-speed op-amp with a JFET input stage. Unfortunately, it was not the most stable of op-amps, and oscillated rail to rail when one of the attenuators was enabled. I tried giving it a little helper op-amp to take some pressure off the poor thing, but that didn't work either. For this next attempt, I did some digging and found the circuit in the datasheet of another part that I was using. I liked it, but I didn't want the variability that came with biasing a JFET with an unmatched JFET. So I found this other circuit that would use a op-amp to keep the JFET at its optimal bias current, and smashed the two together to make this. And this is what the frequency response looked like. It had about 1 dB flatness, which wasn't very good, and the bandwidth was only 235 megahertz out of the target of 350. But this was a start. I thought I could further improve the flatness of the response and get closer to my bandwidth target by combining the front-end modules together into one board. Flatness was better, but still not great, and bandwidth seemed to only be 265 megahertz. This was workable, but I'd be back. A year or so later, TI had released a new buffer chip that was literally made for this. It had high input impedance, low noise, built-in protection, and a whopping 3.1 gigahertz bandwidth. I made a test board for it, hooked it up to my new spectrum analyzer with tracking generator for less janky graphs, and got less bandwidth than before. No peaking, so that mic was peaking. No peaking, so the flatness is very good. But what's going on here? What's limiting my bandwidth? Well, it kind of looks like a low-pass filter with 211 megahertz cutoff. But I only have 10 ohms in series with my input capacitance. That would leave 50 ohms. So how do you test this input when all your equipment has a 50 ohm output? I've done 3 things to convince myself that this input functions as expected. 1, compare the response to a RC filter. If the buffer has a flat response and enough bandwidth, then our overall response should match that of a first-order filter. No peaks, dips, or sudden sharp declines. And it does, up to the new target bandwidth of 500 megahertz. 2, check the response when using a probe with the input. That should check that our impedance isn't going out of whack, throwing off the divider created with the probe. This also looks good. 3, check the response of the 50 ohm path. This should be the truest look at the response of the buffer alone. This resulted in 0.31 dB flatness and 820 megahertz of bandwidth. Beautiful. I see we've smoothly segued to our next topic of the 50 ohm mode. In most of the literature on scope front ends, do check out this book, it's very good. 50 ohm mode is shown as a switch way out in the front of the circuit. But if you do that, you get the same filter as earlier, but with 50 ohms in parallel. This has a 3 dB bandwidth of 500 megahertz, so it's actually fine, right? The other thing we care about in 50 ohm mode is how much signal is reflected when connected to a 50 ohm system. This is caused by impedance mismatch over frequency. Ideally, you want your 50 ohms to stay 50 ohms throughout the whole bandwidth of the instrument. This reflection is measured in a voltage standing wave ratio, or VSWR. Ideally, we'd keep this below 1.5 over our bandwidth. This method has a terrible VSWR of 5.5 at 500 megahertz. Let's reflect on that for a moment and think of a solution. Ideally, you'd want a completely separate path just for the 50 ohm mode. Since I wanted to keep costs down, I use the same buffer for both modes, but I have one path through the relays that has no added capacitance. This resulted in the bandwidth measured earlier. And the VSWR should be under our target of 1.5 over the 500 megahertz bandwidth. Well, that's enough about capacitors to ground. How about a capacitor in series with our signal? The simplest way to AC or DC couple the signal was to put a coupling cap and a switch right by the input. I chose a solid-state relay for this task as it was smaller and cheaper than the dual-pole relays used for the attenuator and 50 ohm paths. The downside of using a silicon switch is it had a lower voltage rating and was sensitive to ESD, and therefore needed a protection circuit in front of it. I really wanted to ditch the protection circuit and solid-state relay for an analog switch at 1/5 the price. This was my first attempt. And that trick cut the bandwidth in half. But the real trick is putting it back together. Ta-da! Just like test equipment manufacturers, a magician never reveals their secrets. But I do. On my first attempt, I put the switch right on the signal path, where it fell prey to the forces of evil, like parasitic capacitance. While in the working version, the signal path is protected from parasitics by the forces of good. In this case, a big resistor. Remember how I said the compensated attenuator would come back to haunt us? Well, I didn't think I could be jump scared by a frequency response graph until I turned on the attenuator and saw this, a giant dip in the middle of our frequency range. To properly exorcise whatever malign spirits cause this dip, we need to see through the resistor divider's disguise and gaze upon its true form. Ugh, horrifying stuff. The truth is, when you buy a resistor, you get an inductor and a capacitor for free, whether you like it or not. And at high frequencies, these big resistors are completely drowned out by these unwanted capacitors, changing the divider ratio. At even higher frequencies, the lead inductance comes into play, but we can safely ignore that under 500 megahertz. So we purposely add capacitance in parallel to drown out the unwanted capacitance. The benefit of this is we can now set the correct divider ratio with these added caps. This is the logic behind the compensated attenuator. But it doesn't stop there. What about the capacitors we just added? Well, when you buy a capacitor, you get a resistor and an inductor for free. But unlike resistors, these extra elements depend on the value of the capacitor. Here's the impedance curve for the 6.2 picofarad capacitor at the top of the divider. Note a familiar looking dip at 3 gigahertz, but this is way over our frequency range, so it's safe to ignore it. However, the curve for the 300 picofarad capacitor at the bottom of the divider has a dip corresponding to the one in the frequency response. At the frequency of the dip, called the self-resonant frequency, or SRF, the capacitor and its ESL, equivalent series inductor, cancel out, leaving just the ESR, equivalent series resistor, of about 100 milliohms, while the top capacitor still looks like a capacitor with an impedance of about 100 ohms. This makes our 50 to 1 divider look like a 1,000 to 1 divider at the lower cap's SRF. I mentioned that the top capacitor still looks like a capacitor. That describes the region of frequencies lower than the SRF, where the capacitor's impedance is greater than the inductor's. While at frequencies higher than the SRF, the inductor's impedance is greater than the capacitor's, making the whole thing look like an inductor. I looked at a few capacitors of the same value in different packages, and they all seemed to have a similar SRF. This didn't seem like a problem I could fix with a component swap. The way I saw it, my problem was the lower capacitor had one impedance curve, and the upper cap had another. So in the same spirit of the compensated attenuator, I added a resistor and inductor to make the top half of the divider have the same impedance curve as the bottom half, which should maintain the 50x ratio of the divider at all frequencies. And that actually seemed to work. Could use a little bit of tuning to get the response to look exactly like the 1x path, but I think I might have fixed it. Let's see how it looks through a 10x probe. Oh, I don't think the probe likes it when the impedance isn't entirely capacitive. I'm still tinkering around with this, but I think it might be time to bring out the big guns. After scouring the dregs of the internet, I found a few families of really fancy RF caps that go past 100 picofarad in value and have a SRF of 1 gigahertz or higher at 300 picofarads. This was the best of them, the ATC 800B series. I haven't tried them yet, but hopefully having something that is capacitive through the whole frequency range will make the attenuator behave a lot better with probes. For this last topic, we're going to need gain. Lots of gain. I chose this absolute wonder of a chip to handle adjustable gain, Nyquist filtering, and driving the ADC. It has low input noise, 900 megahertz of bandwidth, and burns 3/4 of a watt each. But thermals will be a story for another talk. We only hit the maximum gain of 87.7 at the lowest input range. And with that much gain comes noise. But it didn't look bad according to my calculations. All right, you know what comes next. As much as I dreaded debugging yet another issue, it was really cool using the scope I designed to debug itself. The Thunderscope has investigated the Thunderscope and found nothing wrong. And I found out that the spikes you see here are at the switching frequency of the negative 5-volt charge pump. This powers the buffer and is divided down to make the negative bias voltage. I tinkered with the decoupling caps for the buffer and more heavily filtered the negative bias voltage, but no luck. I did, however, get the idea to try 50 ohm mode, and it looked quite good. So what changed? Everything that had an obvious connection to negative 5 volts was out of the question, as it was all shared with the 50 ohm mode. So what could it be? The noise, it's coming from inside the ground plane. Nothing may be coupling to our signal on its way there, but every signal needs a return path through a ground plane. And when you share the same return path with a power plane, you get currents intersecting. The reason it only shows up in high impedance mode is that a tiny 1 nanoamp coupled current into the 1 megaohm input impedance turns into 1 millivolt, which is then gained up by 87 times, and that's a huge problem. While in 50 ohm mode, it would become only 50 nanovolts. This is still just a theory, but I will be moving the power plane to a different layer next rev, so we'll see if it's correct soon enough. And that brings us to the present. I hope you've enjoyed watching me fail my way ever closer to making a great front end. And know that we all feel like this sometimes when we're faced with setback after setback. But the most important thing is to keep trying, keep learning, and keep making. Thank you. All right, do we have